X-ray telescope development is a lot like any other instrument developed for spaceflight. We make small components like reflectors and we test them. We make assemblies including many reflectors and we test that assembly. We make the full-up telescope assembly from those and we test it and we test and we test. Because you have to know it's going to work on the ground because you can't fix it in space. We're making the 5 telescopes for the XIS instrument and the XRS instrument that'll be on board the Astro-E spacecraft.
The telescope mirror manufacturing process begins with raw materials like the metal foil.
The earliest operation is foil cutting and forming. We have to produce upwards of 10,000 foils for the one mission in order to get the 6,800 foils that we need to fill up 5 telescopes.
The technician puts the foils through a special roller.
This is going to impart the gross curvature that we need and the slight bit of conical shape that we want. And then you'll put that stack inside this little window here. This forming mandrel has a cone shape that is the proper prescription for its place in the mirror. While it's still under vacuum and so the atmospheric pressure is pressing them against the mandrel, it takes on the exact shape of that mandrel.
The X-rays that Astro-E2 will observe get absorbed in many materials, including glass and ordinary mirrors. So Astro-E2 and other X-ray telescopes require a unique strategy to focus X-rays onto a detector.
We use an X-ray telescope which depends on a grazing incidence reflection in which the reflectors are nearly edge-on to the X-ray source. The X-ray beam hits the primary reflector, then hits the secondary reflector, and then moves on to the detector about 4.5 meters away. We add a pre-collimator before the primary reflection to block off-axis X-rays. So now they have the proper figure, is what we say. They're curved just right, and they're smooth enough on that surface, but they're still not shiny enough. Then they go down to the replication lab. They've been busy cleaning up the glass mandrels, and then they're put into a gold deposition system, and gold is deposited on that outer surface of that glass tube mandrel. We spray thinned out epoxy on the foil. And once it's in vacuum, that round mandrel is lowered and it just sits on top of the foil.
Maintain my time.
So then we put that mandrel inside an oven and bake it overnight. And it's not a real bake, it's just 40 degrees C. Gold won't stick to glass very well. Through a process that is more magic than anything else, we lift the foil off of the mandrel, and the gold that had been on the mandrel now is stuck to that thin film of epoxy, but the front surface of this foil sandwich with gold on the front has the surface quality of the glass mandrel.
The X-ray telescope manufacturing process enters another phase, testing.
We've now gotten foils that have the front surface we want, and it goes into the metrology lab where the foil is inspected.
A WICO profilometer measures using light, so it's a non-contact method. It uses visible light to actually measure the roughness of the surface. As far as X-rays go, these are pretty close to mountains. But these are very short mountains, being only about 1/1000th the height of a human hair. So we would like to have them just basically as small a difference between the maximum and minimum as practical.
So then they're graded, some are rejected, some are what we call flight, and then some are put in a small class of usable if you have to get yourself out of a jam.
All the parts are ready.
So we're going to start building up a telescope, and we do this one quadrant at a time. After you put the bars in, you put one foil in the middle of the housing somewhere, and you put it on an alignment fixture. The alignment bars are the ones that create the angle and perfectly position the foils in the housing. Make it so that we can stick one housing on top of another and have 175 concentric nestings line up perfectly with 175 below. The mirror team had its share of problems too. Early on we had some structural problems. In a couple of cases, mirror assemblies did not pass vibration testing, which simulates the rigors of launch. We went in and made repairs to the assemblies and retested successfully.
The X-ray telescope quadrants are ready for more testing and final assembly.
You're seeing the edges of the foils in many arcs like that. That's the 175 nestings. So then you got a quadrant. Now we're going to do some optical testing with that, and then we start doing X-ray testing with it. And so what we're looking for is to contain the photons in as small a circle as possible.
The better the focus, the more photons will arrive onto the XRS.
So the process is done again in optical and white light by putting the 4 quadrants on the ring and then looking at where each quadrant projects its image and adjusting these until they all project to the same spot.
With the assemblies complete, the telescopes can be packed and sent to Japan for further testing and final assembly onto the spacecraft.